Chapter 6 is the first chapter where we get to talk about electrical components that don't just, fuck it. Okay. So chapter 6, we're going to talk about capacitors and inductors. Capacitors and inductors are both charge storage elements, so they do not dissipate electrical energy like resistors do. Instead, they store it. So the first is our capacitor, and if you've had physics, you've studied this before. So for a capacitor, draw a chunk here and then split it up. We have two plates. So there's my first plate and another plate. With something in the middle. So in the middle here, we have a dielectric. And it has a permittivity I'm not sure that's spelled right, of epsilon. The two plates are distance d apart, and we have an area A. And we make a point of connection on the top and the bottom of both the plates, and we get a capacitance. So these are our metal plates. And we get a capacitance, C, that's equal to epsilon A over D. And you can look in your book and see a whole chart of different permittivity values. So that's something that's given, it's a material property. What we control is the area of the plates and the distance between them. Well, we as designers. A capacitor looks like a battery, except the plates or the lines are even in length. So remember, a battery, the top one's longer. Capacitor, they're equal. This is our plate that has a charge of positive Q and negative Q. And we have some voltage V that forms across it. And we get Q equals CV. So the capacitance times our voltage. Capacitance is measured in farads, which is a capital F. And if we take the derivative of both sides of that, we get dq by dt equals c dv by dt. Well, if you think way back to chapter 1, dq dt is current. So we get current through a capacitor is equal to c dv dt. Now, what if we integrate both sides? Well, that's going to give us the voltage. So, integrate. And we get V equals 1 over C from some time 0 to t, I dt plus V of t0. So we're going to use that later on in the chapter. Also, want you to remember power. P equals VI, right? If we have P equals VI, then we have P equals VC dV dt. And if we integrate that, we'll get the energy stored in the capacitor. Because if we integrate power, we get energy stored. So again, this is all from chapter 1, these integrals and derivatives and definitions. So if you forgot them, go back and review chapter 1. The energy stored, so integrate to get energy stored, and we get W equals C integral minus infinity to T d dt 1/2 v squared dt. So what we end up with is 1/2 CV squared for the energy stored in a capacitor. A couple of things to note about a capacitor, and one that's really, really important that we'll use a lot in our problems. In DC, a capacitor acts as an open circuit. So if you see a capacitor in a DC-only circuit, you can replace it with an open. Now, why is that? Well, if voltage is constant, then dV dt is equal to 0. If dV dt is equal to 0, then our current is equal to 0. If our current is equal to 0, we represent that with an open circuit, because current can't jump through a big hole, or over a big hole. Our other important thing, which we'll really use heavy in Chapter 7, is that the voltage across the capacitor cannot change abruptly. So that's saying that dV dt cannot be infinite, right? So the voltage across our capacitor takes some time to change. It cannot change instantaneously. That's because it has to charge up